We're going to take this opportunity to dig a little deeper into cyclohexane and its conformations, and we'll see there's some very interesting things we can learn about it. Our learning goals include the interconversion of the chair conformers in cyclohexane and how that interconversion is affected by the presence of substituents, that is, things that are substituted for hydrogens on the cyclohexane ring. So cyclohexane chairs. Remember that the lowest energy conformation for cyclohexane looks a little bit like a lounge chair, and that's called the chair conformation. It has two equivalent forms, and they rapidly interconvert at room temperature, about 100,000 times per second. So we can say that both of them are equally present there and constitute about 50% of the molecules. Now, these look like this, and you look at this, you might say, well, so what? They don't look any different to me, and they aren't. But we're going to find out that, in fact, there is an important subtle difference between them that we can exploit in certain ways. So I'm going to draw these again here, and we're going to talk a little bit about those subtle differences. First, we notice that half of those hydrogens are sticking straight up and down. We call these axial positions on the cyclohexane ring, and they're typified by the fact that they are, in a sense, all parallel in vertical direction here. And if we drew a bond line diagram, we might draw it like this, again emphasizing the fact that all of these carbon-hydrogen bonds are parallel to one another. We also have a set of hydrogens that are not in that same configuration. These are called equatorial hydrogens, and they lie more or less in an equatorial plane as we go around the periphery of the molecule. So again, we might then draw this in a bond line diagram that looks something like this. And you can see that those hydrogens all tend to be kind of in that central plane of the molecule. Well, it turns out that when the conformations change in cyclohexane, the axial positions and the equatorial positions switch places. So focus on the red hydrogen on the far left that's circled. Okay, in one conformation, it's in an equatorial position. When this cyclohexane undergoes a ring flip or a conformational exchange, it now ends up on the right-hand side in an axial position. Similarly, if I start with a hydrogen, the blue one on the left that's circled, in an axial position, when we undergo a ring flip, it ends up in an equatorial position on the right-hand side. So basically what has happened in this case is the two have flipped positions. So we say equatorial has gone to axial and axial to equatorial, and this is going to be true of all of the positions in the ring. All the ones that were axial in the first place are going to end up being in equatorial positions. All the ones that were equatorial in the first place are going to end up in axial positions. So how can we relate this to strain energetics? Why is it that these two axial and equatorial positions, besides the fact that they're geometrically a little different, why are they different in other ways that matter to the molecule? Well, the axial positions have a greater steric interaction with one another than the equatorial positions. And one way to visualize this is to look at these three-dimensional models and show, for example, on one side of the molecule, these are the three axial positions of the hydrogens. They're very close to one another in this position, whereas the equatorial positions are separated by a greater distance from one another. The same will be true of the axial positions on the bottom. They will also be very close together. So if we were to look at the molecule from the top, this is what it might look like. So here are the three axial positions drawn on this picture of it from the top, and they're very close together. And then the ones below are going to be on the other side of the paper, or other side of the surface here, and then the equatorial positions are going to be sticking outward from the ring. Now they'll alternate bending slightly up and slightly down, but you can see that they're somewhat farther apart as a result. So what we have is an enhanced steric interaction between axial positions and a decreased steric interaction between the equatorial positions in cyclohexane. Now, how does that matter from an energy difference? Remember, when we had steric interaction, that usually gave an increase in potential energy. So the way we might draw this is if we have two ring-flipping cyclohexanes going between conformation A and conformation B, where they really are equivalent to one another, but they will end up going over a little barrier to interconvert. All right. I'm not going to worry about the details of this barrier, but simply point out that A and B are both in equivalent wells, so they are at the same energy. They have to go over an energy barrier to go from one to the other, but otherwise A and B are essentially equivalent to one another energetically. Now, let's consider the same thing between these, but now I'm going to put substituents on one, or a substituent on one of the atoms. Let's say it's a very large atom, or it's a bigger molecule, like a methyl group or something like that. Now it's going to make a difference if that methyl group or whatever is either in an axial or an equatorial position. Okay, in the axial position, it's going to be brought into close contact with its neighboring hydrogens. This steric interaction is going to raise its energy relative to the similar situation with the one in the equatorial position. So now, instead of having a nice symmetric arrangement between these two wells, I'm going to see that A is at a higher energy than B because that substituent happens to be in an axial position. So how does that affect things? Well, these chair conformations are basically a distribution of molecules. Some molecules are in one conformation, some are in the other. And if one of those conformations has a higher energy than the other, it's going to have a different population of molecules. In general, we find that the higher the energy, the fewer molecules basically populate that particular conformation. Now, larger groups are going to lead to higher energy differences. So I mentioned methyl and I mentioned a bromine or something on there. It depends on how large that group is that's attached to the cyclohexane ring, but if it's larger, it's going to lead to a greater energy difference. And that means that larger groups are going to have a greater disparity in their population. So what does this look like? Well, for example, let's put a fluorine on. Now suppose we have the fluorine one fluorine attached to one of the carbons in the cyclohexane ring. When that fluorine is in the equatorial position, it's going to be at a lower energy than it is when it's in the axial position. What we see in terms of measuring the populations is that 60% of the molecules show fluorine in the equatorial position, while only 40% show it in the axial position. You should remember, and this is very important, that equatorial is the lower energy of the two, and that's where more of the molecules will be found when you have something other than hydrogen attached to a cyclohexane ring. Okay, let's go to a little bit bigger group. Let's go to methyl. Now we see there's quite a bit of population disparity. When methyl is in the equatorial position, it's 95% of the molecules, whereas in the axial position, it's only 5%. So methane, when you put a methane on a cyclohexane, most of the molecules in that sample are going to have the methyl in the equatorial position. It's even more pronounced when we have something like tertiary butyl group. Tertiary butyl group is like a methyl, but we've substituted each of the hydrogens with another methyl group, so it's a really big group. And when we do that, we find that 99.9% of these molecules have the T-butyl group in the equatorial position. Only 0.1% are in the axial position. So chemists sometimes use this as a device for locking a cyclohexane ring into a particular conformation. If they put a T-butyl group on there, they know that that T-butyl group is going to avoid the axial position, so it fixes the position of all the others.